Think about analyzing a busy city traffic system using only a single photograph. You would miss the flow, the congestion, and the evolution of rush hour. This limitation drives the research in the paper A, Survey of Dynamic Graph Neural Networks, which explores how to bring the dimension of time into graph learning. Traditional graph neural networks are powerful, but they typically treat data as a frozen snapshot, ignoring how systems evolve. Since real-world networks like social media or biological systems are constantly changing, the authors argue that ignoring this time dimension results in a significant loss of critical information. The paper categorizes dynamic graphs into two main frameworks. On the left we have discrete time graphs, which function like a movie strip composed of individual static snapshots taken at intervals. On the right, continuous time graphs treat data as an unending stream of specific events, recording interactions down to the exact millisecond. To model these changing systems, the researchers describe methods that combine spatial aggregators with temporal updaters. This often looks like fusing a graph neural network, which understands structure, with a recurrent neural network, which understands sequence, creating a unified architecture dealing with space and time simultaneously. Deep diving into the mechanics, some approaches maintain a distinct memory vector for every node, effectively giving the graph a long-term memory. The authors also highlight techniques like time encoding to map continuous time into vector space, and even methods where the neural network's own weights evolve over time. This figure illustrates the comprehensive taxonomy proposed by the researchers, mapping out the entire landscape of dynamic graph representation learning. It visually separates the snapshot-based discrete methods from the event-based continuous ones, providing a roadmap for understanding how different architectures tackle temporal data. The implications of this technology are vast, enabling better recommendations in e-commerce and more accurate fraud detection in finance by analyzing transaction timing. However, the authors note significant challenges, particularly the difficulty of scaling these complex calculations and the scarcity of diverse, large-scale public datasets for training. Dynamic graph neural networks represent a vital shift from analyzing static structures to understanding evolving systems. For more details on this survey and the future of graph learning, visit emergentmind.com.